talk to you about this later. This is some kind of a signal processing that is occurring in the recording and in the reproduction. This is 22nd lecture. We complete discrete time Fourier transforms today and we also have an introduction to sampling. You recall last time we ended our class with the modulation property. That is, if you have a product of x of n, x1 of n and x2 of n, the Fourier transform of the product is 1 over 2 pi, the convolution of x1 and x2. Is that right? Or is the 1 over 2 pi not there? Pardon me? What is it? Yeah, but what is the convolution? It is integral over 2 pi, x1 of theta, let's say, then x2 of omega minus theta d theta, and 1 over 2 pi. Okay. The convolution is this integral or 1 over 2 pi times this? Only the integral. All right. Now let's first take an example of this. The example that we take is, we take an x1 of n which is periodic. It is minus 1 to the power n, which is the same as, you better get acquainted with this, e to the j n pi. E to the plus j pi or e to the minus j pi is equal to minus 1. So e to the j n pi is minus 1 to the n. And therefore, if I plot this sequence, I have at n equal to 0, it is plus 1. At n equal to 1, it is minus 1. At n equal to 2, it is plus 1, and so on. So it is a periodic signal. This is 0, 1, 2, 3, and so on. And the value is 1. This is minus 1. This is a periodic signal, and what is the period? Period is capital N equal to 2. All right. If x of omega, if the signal is e to the j omega 0 n, what is its Fourier transform? 2 pi times summation delta omega minus omega 0 minus 2l pi, where L goes from minus infinity to plus infinity. Is the factor 2 pi all right? You must remember this. The factor 2 pi is all right. Okay, each impulse is of strength 2 pi. Now what we have is e to the j n pi, and therefore omega 0 is simply pi. All right, omega 0 is simply pi, and therefore the Fourier transform of x1 of n is capital X1 of omega. That would be 2 pi summation over L delta of omega minus omega 0 is pi, so you shall have 2L plus 1 pi. Let me use a different color. That is what the delta function would be. All right. So if I plot this, if I plot it versus omega, then we have at 0, we have at pi. Do we have at 2 pi? No. 2 pi, nothing. Then we have 1 at 3 pi, and similarly at minus pi, minus 2 pi, that is nothing, minus 3 pi, that would be an impulse. And each of these impulses shall be of strength 2 pi. Not at 0. All right. This is gone. What we have is, we have at pi of strength 2 pi, at 3 pi of strength 2 pi, at minus pi of strength 2 pi, and so on. Now in the modulation property, in the case of the discrete time signals, the integration is to be carried out over one period. So let's choose this as the period, that is 0 to 2 pi, this as the period. Only one delta function occurs there, all right. 0 to 2 pi, only one delta function occurs there, and this is delta omega minus pi, all right. So in the in the interval 0 less than omega less than 2 pi, all right, capital X1 of omega, this is the region over which we shall integrate. Capital X1 of omega is simply 2 pi delta capital omega minus pi. Agreed? And so if we take an arbitrary x2 of n, then x1 of n multiplied by x2 of n shall go to 1 over 2 pi integral over 2 pi, all right, capital X1 of omega, that is 2 pi delta omega minus pi, multiplied by capital X2 of, yes, I am integrating with respect to omega, so capital X2 of, where is theta?
There should be theta minus pi cos theta.
What should be theta? This should be theta minus pi. No.
No. No, sir. Yes.
No. X. Let's recall our integral. It is 1 over 2 pi integral x1 of theta x2 of omega minus theta d theta. All right. So how do we modify our? This is x1 of theta, and therefore it would be delta of theta minus pi. Agreed? X1 of theta. Then x2 of omega minus theta. So we simply write omega minus theta. Pardon me? X1 of omega, I want to find out x1 of theta. So all that I do is replace omega by theta, and therefore it becomes delta theta minus pi, all right. And what do we get here? I have to rewrite this. X1 of n, x2 of n, they transform into 1 over 2 pi. The first thing I write is x1 of theta, and that is 2 pi delta of theta minus pi. Agreed? The second is x2 of omega minus pi, omega minus theta. So I write omega minus theta d theta.
So the limits of integration now should be 0 to 2 pi. Yes, sir. 2 pi would mean any 2 pi.
Yes, that is correct. Is the point clear? The point that has been raised. This integration cannot be carried out over any interval now, because we have taken the capital X1 of omega in the range 0 less than equal to theta less than equal to 2 pi, and therefore the integration limits are no longer arbitrary. It must be carried out between 0 and 2 pi. And you see the result. The result is the delta function exists only at theta equal to pi, and therefore capital X2 becomes what? Omega minus pi, and then under the integral you have delta theta minus pi d theta, which is unity. 2 pi and 2 pi cancel. So this is what the result is, which means that if I multiply x2 of n, an arbitrary periodic signal, x2 of n, by x1 of n, which is minus 1 to the power n, then the Fourier transform of this is capital X2 of omega minus pi, which means that the spectrum is simply shifted to the right by an amount pi. Now, is this a surprising result? We already derived this, isn't it? We already derived that if you multiply a signal x of n by e to the j n omega 0, then it is simply x of omega minus omega 0. And this is the great result that we derived through application of the modulation property. And therefore, it is a verification of the modulation property. All right. Next we look at the use of capital H of omega. You recall that in a linear discrete time system, linear time invariant DTS, we are going back to convolution. If the input is x of n and the output is y of n, then you know that capital Y of omega is equal to h of omega multiplied by capital X of omega, where h of omega is the Fourier transform of h of n, that is the unit impulse response of the system. I write it again, capital Y of omega is equal to capital X of omega h of omega, where h of omega is the Fourier transform of x of n, and by definition this is equal to summation x of n e to the minus j omega n. N goes from minus infinity to plus infinity. I made a mistake.
So
H of n, that's right. This should be h of n. Okay. Now h of omega, as you know, is called the frequency response. It is in general a complex quantity, and the thing you notice is if you can find out capital H of omega, then you can also find out h of n. H of n is simply the Fourier inverse of capital H of omega. All right, and this is one method of finding the unit impulse response of a linear time invariant discrete time system, and this is a much simpler method than solving the difference equation. In the difference equation, you had to find the correct initial conditions and then solve for the system, solve for the homogeneous equation, solve for the particular solution, then combine the two and find out the constants from the given initial conditions. Now, in the most general case, a difference equation can be written as a k y k minus n. In the most general case, it's the other way around, n minus k. That should be equal to summation bk x of n minus k, where k may go from, let's say, 0 to capital N. Here k may go from 0 to capital M, and m and n are not necessarily equal. They can m and n can be constrained by any equality or inequality relationship. All right, there is no control on how many differences shall be involved with x, how many differences shall be involved with n, with y. But we know that capital N, that is number of differences that are required for the output, determines the order of the system. This determines the number of eigen values for the system. All right, you can write a characteristic equation by putting y of n equal to z to the n. You can write an equation in z, and the roots of z give you the eigen values. All right, all this has been done earlier. What I want to tell you now is that if we take the Fourier transform of both sides, then in the left hand side you get ak, and y of n minus k, that is you get y of omega e to the minus j k omega, summation over k, and this becomes equal to bk capital X of omega e to the minus j k omega. Is that correct? So that I'm taking the relationship that x of n minus k, if x of n transforms to capital X of omega, then x of n minus k transforms to capital X of omega e to the minus j k omega. That is the delay, and this shows itself as an angle shift. This is only an angle shift, isn't it? It does not affect the magnitude of the spectrum, it only affects the phase. All right. Now, if I simplify this, that is, I want to find out, my ultimate aim is to find out h of omega, which is obviously y omega by x of omega, and therefore I can determine the frequency response function by inspection of the difference equation. In the most general case, for example, the frequency response function is simply the summation bk of e to the minus j k omega. K goes from, let's say, 0 to capital M, divided by 0 to capital N ak e to the minus j k omega. This is the frequency response function in the most general case, and you notice that if m is less than n, alright, the first thing you notice is it is a rational function, is it? In what? What is the variable? That is right. It is rational. You must define your variable. It is rational in e to the j omega. It is not rational in omega. Obviously it is irrational because there is an exponential power involved. It is not rational in e to the j omega. It is rational in e to the minus j omega. Can you say it is rational in e to the j omega also?
Yes, sir.
Why not? We multiply. We multiply with the required number of terms, and then we can convert it into a rational function in e to the j omega, provided you tolerate a factor, an exponential factor. Is that clear? You have to tolerate an exponential factor. For example, if the numerator is, let's say, 1 plus e to the minus j omega plus e to the minus j 2 omega, and the denominator is simply 1 plus half e to the minus j omega. All right? To convert it into a rational function in e to the j omega, you have to multiply the numerator by e to the 2j omega and the denominator by e to the j omega. Also 2j omega. I must. And therefore, you must tolerate. Pardon me? Okay. Let's do it. We take e to the minus j 2 omega common out of the first, out of the numerator, and e to the minus j omega common out of the denominator. Then I get e to the j 2 omega plus e to the j omega plus 1, and in the denominator I get e to the j omega plus 1. Now, but this is plus half. This is perfectly a rational function. But you see, we are multiplying this by e to the minus j omega.
Yeah, this can be done as 1 by e for j omega.
This is 1 by e to the j omega, and therefore there is no problem. You don't have to tolerate anything. All right? So it can be looked upon as a rational function in e to the j omega by a slight manipulation. Otherwise, it's obvious that it's a rational function in e to the minus j omega. And this shall always be the case because we are considering only finite order systems. Let me point out that if you had considered a distributed system, and in infinite order system, then obviously a rational function would have been out of question. The functions would not have been rational. All right? A transmission line, for example, is not, the frequency response functions are not rational in omega. A transmission line is an example of a continuous time system, and as you shall see, or you might have seen already, that the transmission line frequency response functions, impedance functions, they are all irrational. They involve hyperbolic functions or trigonometric functions. Okay, let's go back to our capital H of omega, which is summation ak, no, this is bk e to the j k omega divided by summation ak e to the minus j k omega. Forget about what? Before we forget about m and n, let's make a couple of other observations. You see, obviously, if m is less than n, then it is a proper rational function. That is, the numerator degree is less than the denominator degree. It's a proper rational function. On the other hand, this is proper rational function. On the other hand, if m is greater than or equal to n, then you see h of omega would be of the form of a polynomial in e to the minus j omega plus a proper rational function. Agree? For example, if the degrees are equal, then your polynomial is simply a constant. You take out a constant, then the numerator degree shall be 1 less than the denominator degree. If the numerator degree is 2 greater than the denominator degree, then you shall take out a constant plus a term containing e to the minus j omega plus another term containing e to the minus j 2 omega, and then you shall get a proper rational function. All right. Accordingly, suppose we take a function like this. Let's say 1 plus e to the minus j omega plus, let's say, half e to the minus j 2 omega plus 1/3 e to the minus j 3 omega, and in the denominator, let's say we have simply 1 plus e to the minus j omega. All right. Then it can be expanded in the following form. You shall have a k0 plus k1 e to the minus j omega plus k2 e to the minus j 2 omega. Do I need one more? This is 3 and this is 1. If they were equal, then I needed one constant. Okay. So what shall I have now? I shall have some constant divided by 1 plus e to the minus j omega. All right. This is an example. You can find out k1, k2, k0, k3. The point that I want to mention is, if you now take the inverse Fourier transform of this, all right, what do you get? You get a delta function. For the first one, you get a delta n. For the second one, you get delta n minus 1. For the third one, you get delta n minus 2, and so on. And for the fourth one, you get k3, what? What is the inverse transform of this? 1 plus e to the minus, yes?
1 to the power un minus.
So it is simply
un.
Is that right?
Yes.
Okay. So this is my final result. You see, if the numerator degree is higher than the denominator degree, higher or equal, then delta functions appear in the impulse response. On the other hand, if it is a proper rational function, delta functions do not appear. All right. Let's take some examples now. The simplest example is yn minus y, let's say a, yn minus 1 equal to xn. This is the first order, a very simple example. And you know h of omega is equal to 1 by 1 minus, you can write it by inspection, 1 minus a e to the minus j omega, and you know what h of n is. H of n is equal to a to the n u of n. Agreed? The simplest example. In all complicated examples, second or higher order systems, we always break it up. If you look at partial fraction expansion is nothing but breaking up h of omega into sum of first order systems. That is, we consider a higher order frequency response function as the sum of frequency response functions of first order systems, and then invert term by term. For example, if we take a second order system, y of n minus, let's say, 3/4 y of n minus 1 plus 1/8 y of n minus 2 equals to, let's say, twice x of n. Then my h of omega, once again by inspection, 2 in the numerator, and what do I get here? 1 minus 3/4 e to the minus j omega plus 1/8 e to the minus j 2 omega. And this can be written as 1 minus half e to the minus j omega and 1 minus 1/4 e to the minus j omega. So what I do now is to expand this in partial fraction. I write a by 1 minus half this plus b by 1 minus 1/4 e to the minus j omega. All right. Then I find out a and b by the usual method. Well, what you can do is multiply this function by 1 minus half e to the minus j omega and then put 1 equal to half e to the minus j omega. Then you find a. Similarly, you find b. And if you do that, the function becomes h of omega is equal to 4 1 minus half e to the minus j omega minus 2 divided by 1 minus 1/4 e to the minus j omega. And you can now invert it term by term. 4, you get half to the power n un minus 2 1/4 to the power n un. Now I can write this as, I can write it in various forms. Let's not is there a problem? Okay. So this is my h of n. The point that I was mentioning is, in this particular example, we were lucky that these factors, half and 1/4, they were real. They can also be unreal, they can be complex. Let us see what happens in the general second order case. We take a difference equation which is yn minus twice r cosine theta y of n minus 1 plus r squared y of n minus 2, let us say, equals to xn. What are the eigenvalues for this system? If you put yn equal to z to the n and simplify, you get a quadratic equation, z squared minus twice r cosine theta z plus r squared equal to 0. So what are the eigenvalues? Don't you see that they are r e to the j theta and r e to the minus j theta, and therefore the factors of the denominator shall now be complex. That is, h of omega shall be 1 by 1 minus r e to the j theta e to the minus j omega times 1 minus r e to the minus j theta e to the minus j omega. I hope I am right. Is it okay? And I can apply the same technique of partial fraction expansion. That is, I write a divided by 1 minus r e to the j theta e to the minus j omega plus b divided by 1 minus r e to the minus j theta e to the minus j omega. All right? And I can find out a and b. Obviously, a and b shall no longer be real quantities. They shall be complex. And if you find this out, I will skip the algebra. If you find a and b out, what do you expect h of n to be? H of n must be a real quantity. Why? Can h of n, you see, if I take the inverse transform of this, can h of n be complex? Why not? The equation has real coefficients, and therefore h of n must be a real quantity. All right. The ultimate result is the following. H of n, I am skipping the algebra, h of n is r to the power n sine of n plus 1 theta divided by sine theta times u of n. That's what the the expression is. The impulse response function is a sinc function. All right, is a sinc function amplitude modulated by r to the power n. You see, this function, this factor depends on n, and therefore it's not proper to say that it's only a sinc function. It's sinc function whose amplitude is modulated by a quantity r to the power n. Sinc function, is this a sinc function?
Yes, so it's a division of two sinc functions.
It's a ratio of two sinc functions. That is the more correct statement. It's a ratio of two sinc functions. Yes. All right. What happens if theta equals to 0? No, but what happens to the eigenvalues? You see, z squared minus twice r cosine theta, they become identical. So it's a case of repeated roots. Repeated roots. And you can either do it by the formula for repeated roots, or you can do it as a limiting value of this, and you can see that if theta equal to 0, then h of n is simply equal to r to the power n plus 1 times u of n. Alright? Another case of interest is if theta is pi. If theta is pi, then what? Then also the roots are repeated, but what happens to the roots? Instead of minus r, they become plus r. And you can verify that h of n shall now be given by minus r to the power n. N plus 1? Un. Now that's very simple to see, right? Okay. So we can handle complex roots, complex eigenvalues also. And that sort of brings us to the end of our discussion on discrete time Fourier transforms. We just look at very briefly before the mid-semester break at this concept of sampling. We have already discussed sampling in the context of one particular example, one or two examples, where it said that we are given a continuous time function like this, an x of t versus t, a function like this, and we said that we shall take only parts of it. We had carried out an example in which we had multiplied this by means of a chain of impulses, unit impulses in the continuous time domain. And we said what we generate is a series of impulses like this whose envelope varies according to the envelope of x of t. And we raised a philosophical question. Do you recall this example? We raised a philosophical question: how is it that the whole can be constructed from parts of it? You see, while sampling, we are taking only parts of it. That is, we are taking an impulse, for example, at t equal to capital T, let's say, an impulse whose strength is x of t. So this process, in this process, if this is 2t, the next impulse shall be of strength x of 2t. The next impulse shall be of strength x of 3t, and so on. Alright? So what we are doing is, from a given x of t, which is a continuum, goes from, let's say, t equal to minus infinity to plus infinity, we are only taking a number of samples. What happens in between, the kind of variation, we are ignoring completely. And we said, through frequency response, through spectrum analysis, that the original function x of t could be reconstructed from these samples, provided certain constraints are met. To look at this in a little more wider context, let's consider examples of functions whose sample values are the same, but the functions are entirely different. That is, in between capital T and 2t, we can have any kind of variation. Alright? So in general, the point that I want to emphasize is, in general, it is not possible to reconstruct the whole only from a part. But if there are constraints, as you shall see, this is one of the most beautiful things in signals and systems, that subject to certain discipline, certain constraints imposed on x of t, only parts of it are sufficient to reconstruct the function. Only parts of it, all other parts, the parts that are used to maintain the character of x of t, are obviously the essential parts. All other parts are non-essential or redundant. Alright? So the sampling is a very philosophical concept, but it is also a very practical concept. You see, there was a time when digital hardware was not as freely available. Microprocessors were not known. Digital computers used to occupy very large rooms, the bulb version and then even the transistor version and so on. So digital hardware was very costly, and most of the signal processing used to be done by analog means. In the 70s, 60s the revolution started. In the 70s, digital hardware became comparable in cost to analog hardware, and therefore many people turned to digital signal processing rather than analog signal processing. And you know that audio, the telephone system, most of them are now digital. And whereas the world, the practical signals in the world are analog. The speech, for example, is an analog signal. It's a continuous time signal. The amplitude is not discretized. All right. Speech is analog. The rainfall is analog. The weather variations are analog. Most of the signals in practice are analog, and therefore there is a need to convert analog signals into discrete signals, and this is done by sampling. In this conversion, if you are not careful, you can lose part of the information or most of the information, and some discipline therefore is needed on the signal itself or the way in which you sample it. But before that, let's look at some signals just to convince yourself that sampling has to be a disciplined processing, a disciplined phenomenon. Let's say we have a signal like this, and we sample it by means of, we'll look at sampling process a little later, but let's say we are sampling by means of an impulse train. So what we are doing is, this x of t we are multiplying by an impulse train like this. And the result would be this chain of impulses whose strength at a particular point, if this point is kt, then the impulse strength would be x of kt. That means that the amplitude of x of t is reflected in the strength of the impulse. The position of the impulse is known. It's at regular intervals of time, capital T. All right. I can have another signal having the same impulses, but it can be quite different. For example, consider this. Okay. This red signal, let's call it x2 of t. If sampled by the same impulse train, shall give you the same sample signal. Isn't that right? Or if you have something like this, or you can think of wild signals like this. Okay? You can have a large number of signals, virtually infinite number of variations, infinite number of signals which are the same sampled values. All right? And therefore, in general, I have made a mistake.
Sir, excuse me.
Yeah.
Multi-valued signals are sampled, like the blue one you have drawn. That's why it is not correct.
Multi-valued, so what do you get, sir, as a sample? You could also
I
get
know, we will not take multivalent signals because that itself is an ambiguous thing. All right. I am sorry, my drawing of the blue one you can ignore. Let's consider the red and green, red and violet one only. I can construct another. I was just not careful in constructing this. This is a multivalent signal. So multivalent signal we take out of consideration. Anyway, the point that I am mentioning is, given this sequence, some sequence of samples like this, you can't say that the original signal is simply by smoothly joining the tips. All right. It is not necessarily the original signal, because the original signal could also be like this. Let me draw another. Could also be the green signal. Okay. The green colored signal, not necessarily a green signal. Okay. So in order that these samples represent the original signal, there must be some discipline. And we have already done the mathematics, so I shall pass over this discussion without making rigorous derivations. Well, what we have is, given an x of t, let me state to start with what are the disciplines, then we will see what the disciplines are. The discipline is that if x of t, sampled versions of x of t, let us say s of t, if this is to contain all the information that is contained in the original signal x of t, then x of t must satisfy two constraints. X of t must satisfy one constraint, and the sampling process must satisfy another constraint. X of t constraint is that it must be band limited. What do we mean by band limited? It means that x of t cannot contain frequencies beyond a certain frequency. That is, the frequency content of x of t, the spectrum of x of t must be band limited. In other words, it exists over one or more bands. It cannot exist at all values of omega, all right, which means that x of t must have you must be able to determine a highest frequency in x of t. The highest frequency omega h must be less than infinity. This is what it means, that x of t must be band limited. And the sampling process, the constraint of the sampling process is that capital T, the sampling interval, must satisfy the relation that 1 by t, which is the sampling frequency, 1 by t, must be greater than or equal to twice the highest frequency content fh. So there are two constraints. One is that the original signal, the signal that you are sampling, must be band limited, and the sampling frequency must be chosen carefully. It must be chosen to be at least twice the highest frequency content. And how this comes about, we had already illustrated in the example that we worked out. Let us quickly recall that example. The example was that x of t was multiplied by a p of t, the sampling function, impulse sampling, where p of t was equal to summation delta t minus nt, where n goes from minus infinity to plus infinity. And therefore, the resulting signal, if we call the sample signal as y of t, then the resulting signal can be simply written as, would somebody object to this? N equal to minus infinity to infinity, I can write x of, no, not here, x of, I beg your pardon, x of nt multiplication by xt, delta function exists only at t equal to nt, and therefore x of nt multiplied by delta t minus nt. This is the sample function. And you know that when two functions are multiplied in the time domain, the spectrum y of omega simply becomes the convolution x of omega with p of omega. All right. We had argued 1 by 2 pi. All right. Let me not make a mistake. Do not allow me to make a mistake. All right. We had argued that p of t, which is a sequence of impulse function delta t minus nt, n equal to minus infinity to infinity, can be, because it's a periodic function, this is where we did the example, because it's a periodic function, we can expand it by Fourier series. And the Fourier series coefficients were all 1 or something else. Now, 1 by t, that is, no, not 2 pi by t. It was simply 1 by t, because within one period only one impulse, and you recall, if you recall the expression for AKs, 1 by capital T integral over 0 to t over t, all right, over the period, the function multiplied by e to the j k omega 0 t dt, minus j k omega greater t. Okay. So the Fourier series has this representation. 1 by t is the Fourier series coefficient for all ak's, and then you have a e to the j k omega 0 t, where omega 0 is 2 pi over capital T. Capital T is the period. Now what you are doing is you are convolving 1 by 2 pi x of omega, you are convolving this with p of omega. All right. Now what is capital P of omega? If p of t is this, then obviously the capital P of omega shall be 2 pi by t. For each exponential term we shall get only 1 delta, because this is a continuous time case, and therefore I shall get delta omega minus k omega naught, where k goes from minus infinity to plus infinity. And you notice that 2 pi and 2 pi cancel, and x of omega, because it is a linear operation, could be convolved with each delta in the summation, and the result becomes extremely simple. The result becomes y of omega becomes equal to 1 by t, don't forget this factor, summation k equals minus infinity to plus infinity, capital X of omega minus k omega 0. This is a result which we had derived earlier, and therefore I had only gone through outline of the derivation. And this shows that the impulse sampled signal has a spectrum y omega, which not only contains capital X of omega, that is for k equal to 0, let us say it was like this. If this was the original capital X of omega, then this is a periodic repetition of this with a period of omega 0, and therefore 0, if this is omega 0, we have a triangle like this, then we have a triangle like this, then we have a triangle like this, and so on. This is an arbitrary hypothetical spectrum, and this is the omega axis. Now obviously if we say this is omega h, the highest frequency content, then this would be omega 0 minus omega h. All right. And if these two are distinct, then obviously I can recover this spectrum. All the information that is contained in the time domain is contained in the spectrum, and if I can recover this spectrum by passing through a frequency domain gate, which simply amounts to a low pass filter here, then obviously I can discard all others, and the filter, the device that I require has to have a frequency response like this, a gate. And therefore I take the sample signal and I pass it through that frequency domain gate, all I get is this, then I take the inverse Fourier transform and I get x of t back. So the recovery of the original signal, this is the discipline, that unless omega h is finite, suppose the signal was like this, let us take a different color, suppose the signal spectrum was like this, which is the spectrum of 1 by, let us say, j omega, then obviously it's not band limited at all. It goes to plus infinity and minus infinity, and I cannot sample it and recover the original signal. That is, a part of this shall not be able to represent the whole. Therefore omega h is one of the constraints. Omega h must be less than infinity. The other constraint is that the sampling must be done in such a manner that these two do not overlap with each other. The two neighbors do not overlap with each other. If they overlap, then obviously the spectrum shall be distorted. And the condition is that omega h must be less than omega 0 minus omega h. All right. That means omega 0 must be greater than twice omega h. And omega 0 is the sampling frequency. I have changed the subscript it should have been omega s, but omega 0, as you recall, is 2 pi by t, 2 pi divided by the sampling interval, and therefore this is the sampling frequency. And this is the great sampling theorem, that if you want to sample a signal, the information content of the signal is not lost, nothing is lost, provided two constraints are satisfied. One is the original signal is band limited, and the sampling frequency is at least twice the highest frequency content. Now, it is also obvious that the filter, that the gate that you are choosing, this frequency, that is the frequency at which the gate cuts off, must also be constrained, isn't it? It cannot lie anywhere. It must be greater than omega h. Omega c must be greater than omega h and less than omega 0 minus omega h. All right? We will continue this discussion next time. Yes.
Shouldn't there be another condition on lowest value of omega in x, in capital X omega, because it could overlap on the other side?
Yeah. Yeah. The question is, should there also be a limit on the lowest frequency content?
Because it may not be symmetric.
Yes. It has to be symmetric because we are only drawing the magnitude spectrum. The magnitude is an even function. No, but the question has a very interesting corollary. How do you know that the spectrum is limited to around DC? Why couldn't I have a spectrum, this is omega, why couldn't I have a spectrum like this? Then what is your highest frequency? This is called a band pass signal, because it's a band centered around some non-zero frequency. The considerations for sampling frequency here are slightly different, and we hope to do a couple of examples in the tutorial class on this. All right. The example that we took for derivation, it was a low pass signal, that is, all frequencies were centered around 0, and therefore we could say the highest frequency content. Here the considerations are slightly different, but we shall continue.